Today, we're diving into the internals of memory, specifically focusing on the stack versus the heap. Understanding where your variable data really lives is crucial for writing efficient and effective programs. This session, part of the Kernel Kafe series, will give you a deep look into how these two memory regions operate, how they differ, and why that matters for your code's performance and reliability. So let's get started and explore the fundamental concepts that govern data storage inside your programs. Your code might be logically perfect, but why is it still running so slowly? The answer often lies in where your data is stored in memory. Is it sprinting efficiently on the stack or struggling in the heap? The memory location plays a critical role in how your program performs, especially during high-pressure execution cycles. They give you an idea of the impact. A cache miss in the heap can cost over 100 times more CPU cycles compared to a cache hit on the stack. This difference is why understanding stack versus heap memory is still incredibly important. Take high-frequency trading, for example. Firms need to shave off nanoseconds from memory access times because even the slightest delay caused by slower memory allocation patterns can mean losing critical trades. Similarly, AI inference engines pre-allocate tensor buffers on the stack to avoid the overhead of heap allocations during inference, ensuring smoother and faster processing. Operating systems also prepare by assigning stack and heap regions to your processes before any code runs, setting the stage for efficient execution. So, understanding the distinction between stack and heap memory isn't just academic. It's crucial for optimizing performance in real-world, high-stakes environments. Let's talk about the stack, which is a fundamental part of how memory is managed in a program. The stack is a contiguous block of memory allocated per thread, and importantly, it grows and shrinks in only one direction, following a strict last in first out order. Every time a function is called, a new stack frame is pushed onto the stack. This frame contains the function's local variables, parameters, and the return address, so the program knows where to go back after the function finishes. When the function returns, its frame is popped off instantly, freeing that memory. One of the great things about stack allocation is its efficiency. Allocating or deallocating memory simply requires moving a pointer, either incrementing or decrementing it, making this process very fast. The lifetime of stack allocated memory is tightly bound to the function's scope. Once the function returns, the memory is automatically destroyed, so there's no need for manual memory management here. It's also important to note that the stack is managed automatically by both the compiler and the CPU. This means programmers don't have to worry about allocating or freeing stack memory, it just happens under the hood. If we look at the call stack, we can see functions like main, compute, and helper stacked up. The top of the stack is where the most recent function call resides, and the stack grows downward toward lower memory addresses. Understanding the stack is key to differentiating it from other memory regions like the heap, but we'll dive into that later. For now, keep in mind how streamlined and efficient the stack is for managing temporary memory during function calls. Now let's talk about why the stack is so fast. The first key point is speed. The main reason for this is that managing the stack involves just a single instruction to move the stack pointer. This makes operations incredibly efficient. Next, consider the size. The stack size is fixed when a thread is created, typically ranging between 1 to 8 megabytes. Because the size is set up front, it helps in managing memory predictably. When it comes to fragmentation, the stack has a big advantage. It's impossible. This is because memory allocation on the stack is strictly sequential, so there's no fragmentation like you might find in the heap. However, there is an overflow risk. If there's deep or infinite recursion, the stack can be exhausted quickly since it has a limited fixed size. Lastly, the stack has excellent cache behavior. It's extremely cache-friendly due to both spatial and temporal locality, which means data accessed close together in time and memory location keeps performance high. These characteristics explain why the stack is often preferred for managing function calls and local variables compared to the heap. Now, let's focus on the heap. The heap is a large area of memory shared by the entire process. Unlike the stack, memory on the heap is allocated dynamically during runtime through functions like malloc or the new operator in C++. This memory remains allocated until you explicitly free it using free or delete. One key difference here is that heap memory can be safely passed between functions, which is not typically the case with stack memory. Allocating memory on the heap comes with a cost. The allocator has to search for a free block of sufficient size, which makes it significantly slower than stack allocation. Also, managing heap memory is the programmer's responsibility, or in some managed languages, a garbage collector takes care of this. The slide also shows a heap memory map, where orange blocks indicate allocated memory and navy areas represent free but possibly fragmented gaps. Fragmentation is a notable issue here. It means that even if there's enough total free memory, a large allocation can fail because the free spaces are scattered and can be merged into one continuous block. Overall, understanding the heap's behavior, its allocation cost, and how fragmentation can impact performance is crucial for effective memory management. Now let's dive into the heap and the trade-offs that come with its flexibility. First, when we talk about speed, managing the heap is inherently slower because the allocator needs to search through and handle free lists. This extra work means allocation isn't as instantaneous as with simpler methods. Next, size is often only limited by the amount of system RAM and virtual memory available, which is a big advantage of using the heap. It can handle large data needs. However, fragmentation is a common issue, especially after many allocate and free cycles. Over time, this can lead to inefficient use of memory spaces. Regarding overflow risk, unlike the stack, the heap avoids recursion overflow. But it's important to note that memory leaks can quietly build up if allocations aren't properly freed. This can eventually cause problems even if they aren't immediately obvious. Finally, cache behavior is another consideration. Because data on the heap tends to be scattered in memory, it negatively impacts spatial locality, meaning the CPU cache is less efficient compared to more contiguous memory like the stack. This can slow down program performance, so it's a crucial factor to keep in mind. Here we have a side-by-side comparison of stack and heap memory, highlighting their key differences. First, allocation speed. The stack is incredibly fast because it simply moves a pointer to allocate memory, while the heap is slower since it involves searching for a suitable block. In terms of size, the stack is small and fixed, limited by its predefined size, whereas the heap is large and flexible, able to grow as needed. Management also differs. The stack is handled automatically by the compiler and CPU, but on the heap, the programmer or a garbage collector must manage allocation and deallocation. Regarding lifetime, stack memory is automatically freed when a function's scope ends, but heap memory persists until explicitly freed, which can lead to memory leaks or fragmentation if not managed properly. Stack memory is private to each thread, making it inherently thread safe, while heap memory is shared among threads and requires synchronization to avoid concurrency issues. These differences are crucial to understanding memory management in programming. Here, we're looking at the process memory layout, which is essentially how the operating system organizes memory for each running process. Every process gets a virtual address space divided into fixed sections. At the bottom, we have the text or code segment, which contains the executable instructions. Just above that is the BSS and data segment, housing global and static variables. Then there's the heap, which grows upwards as the program dynamically allocates memory. This is where things like objects created with malloc come into play. Opposite to that, at the top of the memory space is the stack, which grows downward. The stack holds local variables and function call information. Between the heap and stack, there's usually an unmapped gap to prevent them from colliding. If the stack and heap grow too much and run into each other, the process runs out of memory, causing it to fail. Stack allocation happens automatically with simple local variables that only exist for the life of the function call, and they're freed immediately once the function returns. For example, when we declare integers inside a function, they live on the stack. On the other hand, heap allocation requires explicit management. When you allocate memory on the heap with malloc, the pointer returned needs to be manually freed to avoid memory leaks. Understanding this difference is crucial because stack memory is limited and managed by the system, while heap memory is more flexible but requires careful handling. Here we focus on common failure modes and why understanding locality is key to performance. First, stack overflow occurs when unbounded recursion or a very large local array exceeds the fixed stack size, causing the thread to crash. Next, memory leaks happen when heap memory is allocated but never freed, causing the process to gradually consume more resources until it stalls or is terminated. Then we have dangling pointers, which are pointers still referencing memory that's already been freed. Accessing such pointers leads to undefined behavior. Use after free errors occur when freed heap memory is reused elsewhere, but old code continues to write to it, often leading to serious security vulnerabilities. The crucial takeaway is that cache locality significantly impacts performance. Stack variables are stored contiguously, allowing the CPU's prefetcher to load them efficiently. In contrast, heap objects are scattered in fragmented blocks, causing slow memory access with many costly main memory trips. This explains why, from a performance standpoint, stack usage often outperforms heap allocation despite raw clock speeds. So, which one should you use? The stack or the heap? Let's break it down. Use the stack when the size of your data is known at compile time, and the data doesn't need to outlive the function where it's created. The stack is perfect when you need maximum speed and predictability, especially for small objects. Think a few kilobytes, not megabytes. On the other hand, use the heap when the size of the data is only known at runtime, or when the data must persist beyond the current function scope. The heap is also ideal for large objects or when the lifetime of the data is uncertain. Plus, if your data needs to be shared across threads or modules, the heap is the way to go. Here are 3 essential things to remember. First, the stack is incredibly fast because it simply moves a pointer without any searching or complex management. Second, the heap offers flexibility since it's shared and its lifespan is longer. But this flexibility comes at a cost. It's slower and less safe. Lastly, most common bugs like overflows, memory leaks, and dangling pointers arise from not fully understanding whether you are working with stack or heap memory. So knowing the differences deeply will help you avoid these pitfalls.